Another aspect of amino acids is how they play a role in proteins, particularly in protein turnover, and where are we getting them from? Are they coming from the diet, or do we build them from scratch in our body? Protein turnover is the idea of a balance between how many proteins we make and how many proteins we break. And this balance is critical to have in order not to build up either an excess or a deficit in proteins. Protein breakdown occurs broadly in two cellular locations. Lysosomes contain proteases and digest endocytosed proteins. You will link all kinds of lysosomal enzyme deficiencies with pathology down the road. But another place is to have what we call proteasomes. Proteasomes are critical for destroying particularly abnormally shaped proteins. In order for a protein to be targeted to proteasome, it will require ubiquitination for destruction. Recall that we reviewed this already in cystic fibrosis in the molecular biology chapters, being that in cystic fibrosis, the chloride channel known as CFTR protein is misfolded, and because it is misfolded, it is abnormal, and as an abnormal protein after ubiquitination, it is directed towards the proteasomes and digested, hence causing all kinds of symptoms with exocrine function in the patient. Well, essential amino acids are half of our amino acids that we currently find in proteins. There are 20 amino acids found in proteins, 10 of them are essential. And essential means you need to have dietary sources of these amino acids to function properly. The deficiency of a single essential amino acid will put you in a negative balance for proteins in the sense that you will break more than you can actually make. If you look at the 10 essential amino acids, it will remain to your capacity to memorize those 10 to know them all. Some of them are more relevant than others though. You see the one that has a little star at the top called arginine? That has been a classic point on step 1. Arginine is only essential during periods of growth. And when you're growing, you're making proteins more than you're breaking them. When you're making protein, you're using nitrogen, since the nitrogen is required for the amino groups of amino acid. So we say that when you make proteins, more than you break them, you are in positive nitrogen balance. Remember that arginine is only essential in periods of growth. The others are essential throughout our life. They include amino acids such as histidine, again the precursor of histamine. They include amino acids such as methionine, required for methylation reaction, phenylalanine to make the catecholamines as tyrosine down the road, threonine for glycosylation, tryptophan to make serotonin, niacin, and also you see branched chain amino acids such as isoleucine, leucine, valine. What can you do with this? Basically, know them if you want to do a question that is straight recall asking you about which one is essential. Otherwise, understand the concept that a single deficiency of one of these amino acids, particularly arginine in period of growth, would put you in a negative balance. Talking about that nitrogen balance. Being in balance means you make and break just as much, so that really the amount of nitrogen incorporated into your body every day is exactly equal to the amount you're excreting through kidney and liver function. Negative nitrogen balance then occurs when there is a loss of nitrogen compared to how much we incorporate. When do you lose lots of proteins? Well, for instance, maybe you're malnourished, and a selective protein malnutrition is referred to as kwashiorkor. Do not confuse, it's explained in your margin, kwashiorkor and marasmus. In marasmus, you have a total caloric deficiency. In kwashiorkor, you have a selective protein deficiency. When you have a protein deficiency, you know from your physiology that you will decrease potentially the making of albumin. Albumin being your major oncotic pressure protein in your plasma, it will decrease osmotic pressure or oncotic pressure in the blood. And if you decrease osmotic pressure in the blood, then what is the water gradient like? If you have less protein in the blood, it's as if you have more water in the blood. And more water in the blood than the interstitium creates a gradient for water to leave the capillaries. So you will see generalized edema in situation of kwashiorkor. You will not see that generalized edema in malnutrition that we call marasmus. A dietary deficiency of even one essential amino acid, as mentioned above, is enough to cause a negative nitrogen balance. Of course, starvation would do it too. How about uncontrolled diabetes? What's the deal here? You know, in a diabetic, they don't have insulin. Insulin is the anabolizing hormone. In other words, the hormone that allows you to build things. When you look at hormones such as glucagon, cortisol, epinephrine, they're catabolizing. They allow particularly protein breaking. And the reason we have lots of protein breaking is the idea of trying to do gluconeogenesis, and that is to increase glucose formation so that like this we can actually feed red blood cells and brain cells. Now the issue here is that the diabetic is always doing gluconeogenesis, therefore is always breaking proteins as a substrate of building glucose. Results in two things: the negative nitrogen balance, but also a significant hyperglycemia with abnormal glycation of proteins along the vasculature, resulting in pathologies such as hyaline arteriolosclerosis, which will cause down the road all kind of ischemic damage in any tissue of that patient. Infection is the idea that this time most of your protein breakdown that occurs is to give energy to inflammatory and immune cells that are participating in the infection. If that's not enough, keep in mind that an infection causes tissue damage. Imagine you have an abscess. Well, if that's the case, if you want to regenerate tissue or even make a fibrotic scar, you're going to need to build proteins, and you're going to probably build the proteins faster than you can provide nitrogen, so you'll go into a negative nitrogen balance. These are as many examples that you can match on your exam to a negative nitrogen balance, a situation where the losses exceeds the production. Conversely, you would guess that a positive nitrogen balance would be when you build more protein than you actually excrete. And why would proteins build up? Because you're growing. A child would have a positive nitrogen balance. And do you remember which amino acid is essential only in periods of growth? The same one we use as a precursor of nitric oxide, which is arginine. It's also used for pregnancy. In pregnancy, you have a positive nitrogen balance, and in recovery phases of injury or surgery, as we try and make tissue, providing we provide the proteins, also as a recovery from any condition associated with negative nitrogen balance. It's a little bit like you have a pendulum that used to be on the negative side and then will swing all the way to the positive side, and eventually will just try and re-equilibrate until ultimately you end up again in nitrogen balance.